Well, welcome back, folks. Kind of a smaller class today, but we'll still get through it. I appreciate everyone making it in. Our goal is just to do more review problems. Just going to be a couple days of more problem and solutions kind of stuff that we're going to be working on. And before we get started, any questions at all that folks would like to begin with? Okay, well, some advice on the final exam that's coming up. The final exam is not meant to be kind of a exam that's going to knock everyone's grade down. It's more just a formality. We have to give one in the math department, so it's a good opportunity to just run through the course, get through the exam. And as far as the extra credit opportunity goes, the final exam grade we mentioned before is going to replace your minimum grade amongst these three. But the final exam is the one exam that I would curve in this class. I never curve exams 1, 2, and 3. I just try to make them fair and we take them as they are. But the way I curve the final exam is all depending on where everyone's course grade is right before the final exam. I take a look into the class average as an entire whole. And if I give a final exam that dropped the class average by like say 15%, it tells me it was a pretty tough final exam. And I try to curve it back to 0 so that the goal of the final exam is to not move the average grade of the whole course. So usually it's curved. Sometimes there's problems that are a little bit more challenging than you saw in exams 1, 2, and 3, but that's with the understanding that it is going to be a curved exam. So if you see a problem that just seems pretty tough, just put as much effort towards it as you can. You'll get some partial credit on it for sure, and just move on to the next. Don't let any one problem really stop your flow getting through the exam. Aside from that, there's other extra credit opportunities here. This one is going to expire since all work is due on May 5th, but I'll take any missing work. And I did mention to more than one student class asked for the opportunity to just revise old homework. There's an old homework assignment that you want to go back to and work on, I would take a revision on it. So I think that's a great way to study, going back to old problems. And I'll accept any kind of that work on Monday, May 5th on the latest. So even if you're giving it to me at, say, 10 p.m., right as the final exam ends, it would be accepted. Other things to mention is, if there's a problem on the final exam that is not your favorite problem, maybe you just didn't like it, or maybe your mind went blank on that one problem, it can happen on a 2-hour exam. There's going to be the opportunity to do essentially a problem swap. One exact problem from this section, not a bunch of problems, but one is going to be on the final exam for not extra credit to do a problem swap. And these are the suggested exercises for practice from the textbook. And for more solutions, I want to give the total solution on that set. Here's the solutions to those exercises as well on that document. So if you kind of weird handwriting, so if you can't read that, let me know and I can get it typed out. But this is mostly looking into the even problems and some of the steps on getting to those results. So practice those kind of problems and it'll be pretty rewarding. Even if you solve every problem on the final exam, this is a worthy one to do if you have the time on it, since it's easy to make simple mistakes here and there, and this could shore up the credit on those kinds of simple mistakes. Well, our goal is to just practice with this document more. And we left off on this problem right here. Any questions at all, folks, before we just move forward to the next ones? Okay, so we're in chapter, looks like chapter 7, section 0.2 on this one. If it's an integral like this, much like the one above, it's just a big built-up u substitution, nothing too fancy really. So we want to find a u substitution that's going to work well for this one. But sometimes if you see a higher power there, it's not guaranteed to work, but it's almost like a dead giveaway. This would be a hard problem if I solved u or set u equals sine cubed. It also wouldn't work too well because the power's off on this one. But the problem becomes a lot more attackable if you let u be cosine power 6. So even if I forgot the optimal strategy for picking u, this is a good place to start because if that works, the complexity of the problem is going to go way down through this substitution. So now we'll just check if it does work. The differential du is 6 cosine, or hang on, I don't like what I wrote there. I think I was focusing too much on that power there. In this strategy, you take power 1 on either cosine or sine. I was wondering why I was doing the chain rule out of nowhere. And then the differential is going to be negative sine t dt. So that's probably how we would start this one, just by seeing the form of the integrand there. If this works, then we need to now take sine squared. So we're factoring out one factor of sine. Cosine power 6 is great right where it is, and leave sine t dt in this position. So this is going to take on the role of negative du. Let's write in that just as an extra step for clarity. Negative du is sine t. dt, we have u power 6 here. And so we just make the standard trigonometric identity on this one. Anyone recall another way to write our sine squared t? Exactly. So we're using the identity sine squared plus cosine squared is 1. So just 1 minus cosine squared on this one, which means because u is cosine t, this is 1 minus u squared. And pretty much that's the experience with every integral we did in section 7.2, just about. Sometimes there were integration by parts problem there, but not too many. The last step is write in 1 minus u squared. Essentially, we're just following the color coding. This has been an effective strategy for you. You're welcome to bring colored pens and things like that to the real exam. This one is a full swap with a negative on the outside, du over here on the right. Then we can say that this is, it might simplify a little bit better if we just distribute that negative on the inside, less things to account for. Let's distribute negative u power 6 into the parentheses. So we're going to get u power 8 minus u power 6 du. Then we do the antiderivative, a ninth u power 9. We mentioned before in class, though, if you know you're going in this direction, the very next step is just to write in a cosine. That is an appropriate step to take right here. If you write cosine power 9, that would be totally appropriate. And you put in a minus for the next one, minus a 7th, u power 7, plus a constant. If this is like a 10-point problem, we still could lose a couple points because the concept is we have to return to the original variable t. So we now write this in as a ninth cosine power 9 t minus a 7 cosine power 7t plus the constant. Well, any questions at all, folks, doing that integral there? Okay, well, one down on the list. Let's run through the next ones. Next one doesn't go exactly the same. This one's kind of out of order, but this is just another one of those integration by part kind of methods. Let's write down the mnemonic once more. We use LIATE to tell us what the best choice of u should be. And this one is kind of different because it's like a pattern break. Usually you might have noticed with integration by parts, you almost always set u to x to a power or whatever polynomial might be there. If a logarithm shows up, this is the best strategy this time. U should be the natural log x, and everything else should be dv on this one. So dv is x power 4 dx, and this gets the table started. You might not do it as a table, so if you have a different process for doing this and it works for you, that's totally fine. I'm going to read your work. If everything is logical, you get to the end step just the same. It doesn't have to be by this specific method. But Following this method, the next thing to do is the differential du, which is 1 over x dx. Here, this is the differential, so we integrate both sides. It's like doing a differential equation. We get v is now a fifth x power 5. And you can just check by quickly differentiating this to see if you get back up to the next line. Next step, I'll write in uv minus the integral of v du, just to have somewhere to plug all this stuff in. And then just follow the order on this stuff. Here's how the color coding goes. So uv is going to be, starting with v, a fifth, x power 5, natural log x, minus the integral for v is going to be, in place of v, a fifth x power 5. Du, we have a differential over here we can swap with and throw in times 1 over x dx. And this is where the problem is going to finalize. Just do one more integral, but now it's at this form, essentially, nothing too complicated, just an ordinary calculus 1 integral. Pretty much like we mentioned way back in like the week 1 or 2. This is the major goal of chapter 7, bring everything back to a calculus 1 method somehow, some way. Doesn't always work exactly like this, but it's satisfying when it does. So it's a fifth natural log x minus, let's write in 1/5 integrate x power 4 dx. So a fifth x power 5 natural log x minus another fifth here. Really, it's just doing this whole process once more. So minus a 25th x power 5 plus the constant. And we've done it, folks. That's our for our second integration by parts problem. Does that look right to folks so far? Okay, full disclosure, as we go through the next problems, working with a good amount of insomnia. So if any of the numbers seem a little bit weird, let me know, we'll get them fixed right away. So next problem, it says evaluate the integral. We have power 2, power 3, unfortunate, right? If it was power 2 here, power 3 there, it's an automatic use a u substitution. But anyone see what the method should be for this problem in the form it's in? Exactly. Sometimes a square root is a good indication. If we can't use u substitution, it should be our first track. But if that's off the table, it's going to be a u substitution method. So next thing we have to do is pick the substitution. Plus inside here is a good giveaway. That's a tangent substitution. If it's a minus, you want to look into between either a sine or a secant substitution. But let's cite the table as well. It's part of our notes to review how to pick these. This is the real last sheet of the final exam. And if you see a problem like the one we're looking into, just take a peek at this. You might tear off the last page of the exam. I made sure the page numbering is correct for that. And we're going to analyze it this way. Because of the plus, that directs us to the tangent here. And it means we'll also be using this identity almost assuredly. So let's start by saying x equals, the variable here is like the a squared, so it's telling us just to take a square root. So use 2 tangent theta. Now, it becomes a process after this. Once you get x, you absolutely want to look into all the other parts, dx being a really important portion. Dx is, again, another differential. They show up a lot in this class, even more in Calculus 3. The differential here is going to involve the derivative of this one. Tangent theta differentiated is secant squared theta. And because it's a differential, throw in d theta. Next part, you might have done a lot of these and decide I know exactly what that's got to come out as, but it doesn't hurt to be a little bit careful. Let's write out some algebraic steps. It's 4 plus x squared, so we're going to square 2 for 4. That's why we wanted a 2 there, to match up the 4 and the 4. Tangent squared theta. Factor out the root 4. This is helping us know exactly what coefficient's in front now. 1 plus tangent squared theta. Then use the highlighted identity in the table. Really, we've been using these identities several times already at this point. And we've got 2 root secant squared theta, which becomes just a 2 secant theta. Absolute values dropped on this domain because cosine's positive on that domain. So is secant. Well, everything is in position. We now just import all the information on the right back into this integral. Really the same sort of process as before, except the way we did the substitution was kind of an inverse process. So if we're going to cube x, we'll have the cube of 2 tangent theta, 8 tangent cube theta. Denominator is that root we worked out, which is a 2 secant theta. And dx, because we took the differential, we can now just swap in all of this stuff, 2 secant squared theta, d theta. Once we're at this part of the problem, it starts to resolve a little bit better for us. The 2 here cancels. Secant comes down to power 1 now. And so let's reanalyze this as integrate 8 times tangent cube theta, secant theta, d theta. So the original integral is complicated because u substitution just doesn't work out for these powers. But now it's just back to section 7.2, trigonometric integral. The complexity is coming down bit by bit. We need a u substitution. We solved one of these kind of problems already on these notes. It's either going to be, I shouldn't use blue again. This is either going to be a tangent or a secant. Anyone see the good option for this one? Let's imagine if we did tangent. du is going to involve secant squared. We only have secant power 1. So yeah, it looks like secant, best option to go on this one. Also, the derivative of secant is secant tangent. That leaves an even power tangent here, and that's the ultimate strategy. Leave even powers, so these identities can be leveraged against the problem. So if u is secant theta, du becomes secant theta, tangent theta, d theta. So let's reorganize the integral to see what's left out, what has to be re-expressed. We drop this down to tangent squared because we're giving away one factor. And then go times secant theta, tangent theta, d theta. So already right here, we get to swap in just a du. The problem became a lot less complicated. Tangent has to be written in terms of secant, but the recipe is right here. Just rearrange the equation. And tangent squared theta is secant squared theta minus 1. So this whole part right here is now, well, it is secant squared minus 1, but let's do even better. That means it's u squared minus 1, going with the original u substitution from the very top. So we're just going to integrate 8 times u squared minus 1 du by those 2 substitutions. So now the complexity is dropping down enormously. We're just integrating a polynomial function. The downside to all this is we have to unwind every substitution that we made. So sometimes that's the more careful end of this problem. Let's write this as 8 times a third u cubed minus u plus a constant. And now the adventure begins. We have to first get some extra space, throw in what u was. So in position of u, we have 8 times a third secant cubed theta minus secant theta plus a constant. Now, the bigger one to unwind is getting back to variable x. So we go to the very top. We're just citing the original substitutions we made when we undo them. And this was one substitution made originally. If x is equal to 2 tangent theta, it implies immediately that tangent theta is going to be x divided by 2. Here's where the right triangle trigonometry becomes relevant out of nowhere. We can now rewrite this as a tangent is always going to involve an adjacent side divided by an opposite side. So build a really fast right triangle. This is helpful to visualize. I think most people find this is a good way to tie the information together. If 8 is there, then the adjacent side is down here for x. The opposite side is over here for 2. And if you like that mnemonic, let's cite it one more time. It was SOHCAHTOA. It's kind of weird. This is a mnemonic you might have learned in middle school or maybe high school somewhere. Oh, it should have been, oh yeah, opposite over adjacent. That's a helpful acronym right there. Thanks for spotting that one there. We're gonna have to flip on the triangle and go opposite over adjacent side. Thanks for spotting that. Good use on the acronym right there to get the right value. Opposite side. Sorry, say again.
I don't know if that's right.
Yeah, thanks for looking into that. We have x over there, 2 down here. And now if we use Pythagorean's theorem, it's root 4 plus x squared. And there's a good check here for consistency. That has to be the original integrand somewhere, and it showed up right in that spot. All we want out of this is secant. Let's write it in the margin. Secant theta is adjacent. Well, it's the reciprocal of adjacent divided by hypotenuse using the cosine side. So take the hypotenuse, root 4 plus x squared, divide by the adjacent side 2. So that's going in here and here, finalizing the problem. We could distribute as well as we'd like, but this is all up to you. I'm just going to leave it factored out. 8 times cube this. The numerator is going to be 4 plus x squared power 3 halves. The halves came from the square root. Denominator is 8. Now it's tempting to distribute 8 inside to simplify it a bit. Minus. Oh, thanks for spotting that. 1/3 would give us a 3 down below there. Good eye on that one. So 3 down below here. And I just about wrote in secant, but we were writing in actually root 4 plus x squared over 2 plus a constant. And if you ended it right there on a real final exam, that's totally all right with me, but let's distribute in to get a slightly nicer looking answer. 4 plus x squared power 3 halves thirds minus, this is going to be, after simplifying, 4 root 4 plus x squared plus a constant. So kind of a rough adventure of a problem, but if this is a real problem on the final exam, the thrust of this one is really the trigonometric substitution. So if you do this all right and get down to this integral, let's say it's a 10-point problem, that could be as many as 6 points partial credit already there, because that's the main drive of the problem. And any further progress, this being a big part, just undoing the substitution, is the remaining points on that kind of question. Well, any questions at all, folks, on our trig substitution problem of the day? Somehow this is problem 2. The ordering on these notes are kind of random in a way. Let's give the next one a try. They seem to get worse and worse as we go, but that's because we're moving through chapter 7. Prior problem was trigonometric substitution. Now this one is partial fraction decomposition. It's been a little while, and this is kind of a tougher one, but again, some of the problems on the exam might be a little bit tougher, certainly not every single problem. If this is a final exam problem, then it would be one of the slightly tougher ones. Only because this is case 3 in the decomposition. X squared plus 1 is going to involve a slightly more involved decomposition. Let's write this in by starting with x squared minus 3x plus 1. X multiplies x squared plus 1. And first we look into the factors. This is degree 1 linear, so we get a over x. This is quadratic, and it's also irreducible. It's just a fancy algebraic way to say can't be factored. That means the numerator becomes a bx plus c over x squared plus 1. And the check on everything you write is the degree of the denominator has to be exactly 1 more than the degree of the numerator, and you're on the right track for this. Well, unless there's repeated factors that can mess up that kind of pattern. So this is a case 3 decomposition. From here, next step we take is clear denominators, so x squared minus 3x plus 1 is a times x squared plus 1 plus bx plus c times x. Now we just pick our favorite method. We've looked into two kinds of methods, picking specific values of x and then solving for the coefficients, or just full on equating coefficients, setting up several equations to solve all at once. I'd say this one is kind of a tie. Both methods are going to take about the same amount of time because there is one really good value to pick for x. It's 0. If you pick x as 0, you can solve for a immediately. So let's try out this strategy. Set x to 0. We're doing that everywhere x exists on the equation, left and right hand side. So 1 is now equal to a times 0 plus 1 plus 0. So we've got a coefficient already. A is 1. Now it gets a little bit tougher if we went this route because there are no other key values to pick. That's because x squared plus 1 was irreducible. But the next friendliest values for x might be positive 1, negative 1. Let's try those out. If x is positive 1, then we'll have 2 minus 3, so negative 1 on the left equals. We call a is 1, so we can just drop a 1 right here. As a reminder, we didn't actually forget about it. So it's 1 times 2 in this position, plus. If x is 1, this is having no effect, and it's just b plus c. So let's add 2 to both sides, and we have the equation 2 equals b plus c. Let me try adding 2 again. 2 plus negative 1 is going to give us, or rather subtract 2. Equation solving is hard today. I'm going to blame it on the insomnia. Negative 3 equals b plus c is my third answer on that one. Does that look right to folks so far? All right, let's pick another value. Negative 1 is the next easiest thing to throw inside here. At negative 1, we're going to get 1, so 2 minus 3. So still a negative 1. Let me check those numbers. Yeah, that's a negative 1 squared. Hang on, let me try again. I have a 1. Negative 1 here is going to give us a plus 3, plus 1. So 5 here, pays to go carefully. Negative 1 here is going to give us 2 times a, but a is 1. So 1 times 2 again. And negative 1 here, I'm going to move the negative just in front. And now we have negative b plus c. So let's do a little bit more surgery on this equation. We have 2 over here. Let's subtract 2 to get 3 equals. Distribute that negative sign. B minus c. That doesn't look super encouraging, right? We have 2 equations and 2 variables, except look at the signs of these coefficients. We have nice opposite signs, so we can just stack these equations together, bring them to one spot. This is essentially doing linear algebra without the matrices now, solving a system of equations. If you have done linear algebra, you can just literally write down a system of equations, do the row reduction, and solve this just as well. But here, now that equations are stacked, add them together, we get 0 equals twice b, because c falls out, we have 0 copies of c. And this now tells us b has to be 0. So we're getting there. We have a coefficient a. We have a coefficient b. It's taking some work, but this is, hang on, let me recall, a case 3 decomposition with the irreducible. These always took a little bit extra work when we saw them. Having a value for b means go to any equation here, just plug it in, and you get the other value for c. So 3 equals 0 in place of b minus c. That gives us c equals negative 3. And those are the 3 equations that we wanted. So we can now take this original integral from the very beginning. Let's bring it down here. It's equal to a over x plus bx plus c over x squared plus 1. And now it rewrites as A is a 1 right here. So 1 over x in the first spot. B has been annihilated. It's set to 0. And C is a -3. So let's go -3 over x squared plus 1 dx. It's kind of interesting in this problem that it's actually the algebra that's the hard step right here. Running through all the algebra gets us to this, but the calculus is immediate now. Antiderivative of 1 over x is the natural log of absolute value of x minus 3. Antiderivative of 1 over x squared is just tangent inverse x. Add the constant c, and that's our total answer on this one. Definitely don't do the algebra as spotty as I did. Go a little bit more carefully and slowly, and then everything really goes smoothly once we bring it all back together. Well, any questions, folks, on the case 3 decomposition here? Okay, so looks like we're nearly done with this chapter 7. There's a couple more things we want to look into for integration. And this one is kind of a challenging one. Let's take our time breaking down problem number 4. We've done these kind of problems in the past in our section. I believe this was 7.8, I believe, improper integrals. This one is a type 2 improper integral because there's no infinities here. However, the upper limit of integration 3 causes a discontinuity due to that denominator. So we can start off by saying, here's where we're integrating on. We're continuous at -1. That's just 1 over root 4. But right at 3, we have a big problem. We lose continuity there. So on this number line, we have to now force a limit into this problem, see if the limit exists. And if it does, we'll say the improper interval converges. So we take a new variable t. T is heading towards the discontinuity. And at the same time, t has to be within the interval of integration, which was from -1 to +3. So we had a problem right there on that upper limit. What we need now is to rewrite this as it's a limit as t heads to 3, but the way we head to 3 is highly specific on these kind of improper integrals. It's coming in purely from the left-hand side. And it makes sense, right? We can't put anything larger than 3 inside of here because we would have a complex number at that point. We have never attempted to integrate complex valued functions whatsoever. So it really has to approach specifically in that direction. So now we're integrating from -1 to t, this whole thing right here. And we can rewrite this using exponents as it's really 1 over 3 minus x to power 1/2. So bring it into the numerator, 3 minus x to power -1/2. And that's, if it's a helpful strategy, a good way to see this integral. Just don't forget, chain rule comes into play on this one due to that negative sign. Easy thing to miss on this one. But this is the hard part of the problem, I'd say. Just getting the setup in place before we proceed to the next steps. Any questions at all, folks, on getting this limit here, put in those positions? Okay, let's run through the next steps then. On the next step, because we're doing an antiderivative of something that is degree 1 on the inside and just an exponent on the outside, let's put in a little bit of extra space before the limit. As t goes to 3 from the, nope, let me try again, goes to +3 from the left. And antiderivative, where we're at on the red dot, goes 3 minus x, increase the power by 1. It's now power 1/2. Multiply by the reciprocal of that power, 2. Take into account there's a chain rule process here. Include that extra negative sign. And this is the right antiderivative. If we differentiate this, 1/2 comes down, wipes out the 2. We subtract 1, so it's -1. And we also multiply by the derivative of 3 minus x, which is -1, canceling that negative sign. So we've got the right antiderivative. We just need to evaluate from -1 to t. So we're on our way. When we did this one as an exam problem, the easiest way people got mixed up on the limit was not actually doing this evaluation part right here. I promise you there'll be plenty of time to do this. I'm only going to write an exam that's about an hour and a half in length, giving you time to check your work, write in steps. And this step is all about making sure we get the limit and everything else down very correctly. So write in -2, limit, t goes to -3. This is the neglected step right here, which made the computation pretty hazy and confusing on the exam. I'm just going to convert this to a square root, throw in the upper limit t. So root 3 minus t minus, throw -1 inside here, root 3 minus -1. And that just helps our brains see what's going to result, if it's going to converge or diverge. But more importantly, it's all about making sure we get that limit just right. T is going to head towards -3, and I forgot, from the left specifically, so we don't have negatives inside the root. Oh, thank you. I had the negative on the wrong spot. 3 from the left like that. Thank you. I was looking at those numbers, getting concerned. But nothing super interesting happens, right? The closer t gets to 3, the closer this gets to the square root of 0. And the limit, it is square root of 0. Whole thing goes to 0 as t goes to infinity. So that part's just gone. That means we're looking into -2 of 0 minus the root of 4. And square root of 4 is just 2 here. So this is -2 times -2, or +4 on this integral. So it's a weird integral. It converges exactly to +4. Also, what this is saying is, if t is right here, it's probably something like 3.9. And the closer t gets to right there at the discontinuity, the closer and closer we're getting values for. In the limit, it's exactly 4 from this part right here. So even though it's a short problem, it's notationally dense. This is a good one to just study, train your eyeballs to what all the meanings are for the symbols, making sure you put the negatives in the right spots. Don't put in the -3 like I did. 3 power -1 makes all the difference on this. Then you're on your way with this. It's not going to be a big blown up problem with lots of like trigonometric substitutions. I'm going to make this kind of question be really about the dealing with the method itself, less about crazy techniques in the middle. Any last questions at all, folks, running through this problem? Okay. Other things we did in this section was Simpson's rule, trapezoid rule. And we gave out some really big hints about this. It was trapezoid's rule on the exam 1, I believe. So you should expect Simpson's rule on the final exam. It'd be weird to change that pattern. It'd be like a trick question at that point. So let's try out a Simpson's rule ourselves for the sake of review. But this is like a built-up problem. There's really 2 sections we're looking into. We have a function y equals sine x, and we want the length of the curve defined by this function. So we can't just launch into Simpson's rule. We need to know the formula for the length of the curve as well. So this is a section 8.1 problem at the same time. So let's go through this one kind of carefully. I think we've got enough space to write this out. First, for the length of the curve, we need the formula. Length is an integral from 0 to 2 pi, the bounds that they gave us on the variable x, and we'll integrate 1 plus dy dx squared dx. So that'll give us the length of the curve. Part B is asking us to do something else, area of the surface. So we'll come back to the formula on that one in a minute. But first, we're going to actually approximate this area, this length right here, through Simpson's rule. First step is then set up the integral. So if y equals sine x, then dy dx is going to be cosine x. Then next step, 1 plus dy dx squared is 1 plus cosine squared x. And this is almost tragic, right? If it was a minus right here, that might be a good problem, except we might have to change the limits of integration so we don't have negatives with the absolute value. But with the 1 plus cosine x squared, we're kind of stuck on this one. That's perhaps the reason we're approximating this, not trying to calculate exactly on this exam. So this now tells us that the length is a definite interval from 0 to 2 pi, square root 1 plus cosine squared at x dx. And this takes us to step 2, where we're going to approximate it this way. Length is approximately equal to, the symbol we used for Simpson's rule was s. And we gave it a subscript to say how many subintervals, so S4. Next strategy is just to write down the formula. Simpson's rule is that delta x divided by 3, multiplying f at x naught, coefficient 1 to start, then a 4, 2, 4, 2 ending on 4 pattern. So 4, f of x1, 2 f at x2, 4 f at x3. There's where the 4 will end, since we're now on, if n is 4, we end at f at x4 with coefficient 1, just like the start. There's 5 values, so that's typical. It seems kind of weird when n is 4, but you have 5 terms, but that always happens for Simpson's rule, trapezoid rule. Any questions so far, folks, with this setup? Well, we've got the formula down. Next thing we're going to do is just going to re-represent some of these parts. Delta x is always upper limit of integration minus lower limit, divide by number of subintervals. The formula was b minus a over n. In our problem, it's 2 pi minus 0 over 4. So it's a pi over 4 on this problem. Oh, thanks for spotting that. 2 pi over 4 or pi over 2 simplified. And once you get your delta x, that's a good next time to get all these values down the line, starting at x naught. X naught's for free. It's the lower limit of integration. It's the a value, which is 0. And then once we have delta x, we just add delta x to get to all the next successive values. So pi over 2 here, pi here, 3 pi over 2 here, and then 2 pi here, adding in those values. And the thing that's probably the most confusing about this is it's very tempting in this problem to call f of x sine x. But that's not the integral we're actually approximating. The f of x in all these spots here is that integrand. Looks kind of built up and annoying, but really it's not too bad. At this point, we're pretty much there. Length is going to be approximately equal to pi over 2 in this position, divide by 3, it's going to give us pi over 6. Now we're just plugging in values. Plug 0 inside here, and there's lots of ways you can write this in. If you gave me root 1 plus cosine squared 0 and left it there on paper, I'd say that's okay. But cosine 0 is 1. 1 squared is 1, so at the input 0, we're just going to get square root 2 on our very first term. So let's go root 2 if you decide to go that route. Then next is going to be plus 4. Next input is pi over 2, and I'm completely fine with this kind of problem, writing in root 1 plus cosine squared at pi over 2. But we do know cosine at pi over 2 is 0, so this is kind of a nice rigged problem. That means it's just root 1, which is 1. So it's just easier to write in by hand times 1, a little bit faster even. Then go plus 2. Now we're at pi. Cosine pi is -1, so the square is back to +1. This evaluates to root 2 altogether, right at pi. So 2 root 2. Then finally plus 4. 3 pi over 2 is a nice value, so is pi over 2. Cosine at any odd multiple of pi over 2 is always 0. So that's just a square root 1, which is just a 1 again. Last one at 2 pi. This is kind of like a trigonometry review problem, essentially. At 2 pi, cosine is a 1. So this is just root 1 plus 1 squared plus root 2. Let me try to match up the color coding first. So that's the approximate length. We did some evaluations If you left it with the entire function and just the inputs, I'm completely fine with that. And we made this statement before in our content when we're doing this for an exam question review. If you leave it just on this form, I'm totally okay with that. Any extra work you do here is just you determining if this is even a reasonable answer. Let's plug it into a calculator and just get a value out. So we have pi over 6 multiplying square root 2 plus 4 plus 2 square root 2 plus 4 plus, it might have been easier if I just combined those, but let's put it all in, plus square root 2. Let me check my numbers here, so they look kind of suspicious. So I've got a root 2, a 4, a 2 root 2, 4, and another root 2. Might have combined like terms to speed that up, but we've got a length of about 7.2 units. So that's the approximate length on this curve right here. For any problem, I think we mentioned this on this content as well. I think this might have been on exam 2. But any problem that involves any kind of geometry like this, length of a curve, surface of a curve, parametric equations, I often do put in the plot. And the purpose of that is just to gauge how reasonable is your answer. So just to emphasize that, let's plot the function and throw it on here. Y equals sine x on domain 0 less than x less than or equals 2 pi. So we're looking into that, and the length of that interval, well, it's about 6, and the fact that it has a curvature says it should be higher in our estimate right here for the length. The exact estimate might be higher still, but this tells us 7.2. It's in the right ballpark for what we would expect on the length of that kind of curve. Well, any questions, folks, on getting through part A? Okay, this problem is really reviewing multiple concepts at once, lengths of curves, as well as dealing with Simpson's rule. And occasionally on final exams, you might see problems like these. They're meant to be fast concept questions where I don't want you to do the full integration. You might have already done enough integration on this exam already. This is just a setup and then stop kind of problem. We're going to rotate the curve C about the y-axis. That's going to give us a surface area as that happens. But really all we do is say, we're rotating about the y-axis. It's 0 to 2 pi. 2 pi, let's think about this. Y-axis gives us a radius x as a variable. Root, grab the same exact function, 1 plus cosine squared x, dx. I recall this being a pretty tricky problem, deciding, should it be a y? Do we leave it as a variable y or should it be an x? So let's cite the notes on this one. This is going to be provided on the real exam somewhere. Here it is on this definition. That's probably a bad spot. Let's put it down below right here. And the information says for a rotation about the y-axis, we'll have an x in this position. I'm not going to give those weird problems where the role of x and y is reversed. Instead of a y equals f of x, it's an x equals g of y. So it's either going to be 2 pi x for y-axis rotation, or it's going to be 2 pi y, and this one is going to be for the x-axis rotation. Let's double check. We did the y-axis. Well, any questions at all, folks? Running through this one? That's good color coding there to tie together. Okay, let's move on to the next one then. This one is asking us to solve an initial value problem, problem number 6. We've done a good amount of these. This one is from section 9.5. Our process for this one was first determine if you have to do extra work. If there's a coefficient 1 and you differentiate that, you would have a 0 right here. The fact that there's a negative sign tells us we're already off. Just to explore that concept a little bit further, I'm going to rewind this, but this would be the easier problem because on this one, the derivative of x would be the 1 right there. We can just reverse the product rule right at this step and solve the problem pretty quickly. But the fact that it looks like this means we have to use the integrating factor, which, I mean, if it's a review problem, we should use integrating factor just to review all the concepts around this. So step one, an integrating factor, is to ensure there is a coefficient one here. It's kind of a dramatic arrow, but this is an easy mistake to make on this kind of exam. If we're going for an integrating factor and there is an x there or an x squared, we have to, as a very first step, divide it out on both sides of the equation. Once we have a coefficient one, it reveals the p of x function. So let's call this step two. P of x is just -1, so a constant function. The p of x function is whatever is the coefficient to just the y function here in this linear equation. Once we have that p of x, the integrating factor, which we call I of x for short, is a base e exponential integrating your p of x function with respect to x. So we solve this interesting integral problem, but it's rapid. We get just e to the power -x, and we never go plus c. We want the simplest antiderivative that's going to work on this one. So take your e -x, multiply it into both sides of the equation, and that forms our step 3 in the process. So right over here, we have e -x, y prime, then minus e -x, y. We're multiplying e -x here. If you wrote e -3x, that's a good shorthand, but just to emphasize what step 3 looks like, let me make that exponent seem less strange. Here's what it would look like right as we multiply. Then that check that we mentioned at the very beginning to determine if we really need the integrating factor, we should just do it again, check for consistency. If you differentiate this, derivative of e -x is itself, and the chain rule is derivative of -x. That's where the -1's coming from. So this does work out as a derivative check, following the arrow exactly in that order. And so we do the pretty weird step, but after you've done it a while, quite a lot, it's not so weird. This is just the product rule. Take e -x, y, if you differentiate that, it produces exactly the terms right above. This is the whole idea of the integrating factor. It produces the unique function, which will unwind a product rule based off what's provided here if the coefficient is 1. So really kind of weird logic on this thing. On the right-hand side, it's e power -3x after combining. Then we just immediately integrate both sides with respect to x. Any questions so far, folks, to this line? Okay, there's often, I shouldn't say that, there is always, following this process, an immediate integration. The left-hand side, antiderivative of the derivative is just e -x times y. Here we integrate as usual. This is a degree 1 function inside the exponential. So best way to integrate is write in e power -3x. If you differentiate -3x, you get a -3. So we put in a -1/3 to counteract the chain rule in our verification. Add a constant. And I almost forgot about this. Now we're solving for that coefficient c through the initial condition. But does that make sense, folks, on how to get from the differential equation to the equation next? Okay, let's bring in that initial condition down. This initial condition says x = 0 implies y = 1. So we use these as ingredients to plug into this equation. It must check as true because we're requiring our curve to pass exactly through that point. So coming back here, we have e power -0 times 1. -0 always looks a little bit weird. Let's just take that off so it doesn't seem like some confusing symbol out of nowhere. Times -1/3 e power 0 plus a constant. So x's are zeros, the y, only one value gets set to 1. 1 is -1/3 plus a constant. So 4/3 is that constant c. We're essentially done, but this type of differential equation is always going to allow us to solve for the explicit solution y. So multiply both sides by e to the x. Y equals e to the x times -1/3 e power -3x plus the coefficient c we just solved for, which was 4/3. Left in this format is completely fine. If you distribute it through, you might decide to write it as y equals -1/3 e power -2x plus 4/3 e to the x. But honestly, they're just as good in either format, I'd say. It's up to you how you'd like to stylize your answer. But we did it, folks. That's our, again, interesting differential equation. It didn't look like it's complex or involved, but there is a good amount of steps to solve even on this one right here. Any questions at all running through that full process? Okay, we've got about 11 minutes, and I'm noticing next chapter is sequences of series. How about we get a good separable equation to go along with this one? That might kind of flow better before we go to our next review set. Does that sound right to folks? All right, let's bring the question up. I've got to have a separable one. Let's see if we can find it. I'm not too sure why I didn't put them together. If we can't find one, we'll just definitely make one up. Hang on, that looks pretty, no, that's a length. Okay, the reason I want a separable equation is, here's a separable one. I'm pretty sure I put one down on the exam, so let's bring this up to the top. It's going to look a little bit weird on the notes, but I'll correct it up a little bit. And let's solve this one with our remaining time. Okay, these pair well. So here's our now separable. Differential equation. Last equation was an initial value problem, so we were looking for a specific function. But this is just a general differential equation. Just like the last equation had a pretty touchy first step, so does this one. Anyone recall what the pretty touchy first step was for this? Good call, absolutely. It's not going to separate nice if we leave it in prime notation. So just as you said, change to Leibniz. dy dx is xy, x squared plus 1. Now we separate these things out according to the variable, bring y with dy, x with dx. This tells us what our next steps are algebraically. Divide y into both sides. So 1 over y dy. Multiply both sides by dx. So that x over x squared plus 1 dx is our right-hand side now. At this stage, it's separated, and then we just immediately integrate both sides. But there's some commonality in the strategies. For this one above, you want to unwind the product rule, then integrate. This one, you separate and then integrate. So left-hand side is going to be really rapid. That's just natural log absolute value of y. That's the left-hand side. Right-hand side is pretty fast too. That's just a u substitution, right? Let's work it out on the right like this. Integrate x over x squared plus 1. You might already know the answer. If you were putting a u in, this would be a 1 over u, and that means it's a natural logarithm. So if you can unwind what this is, in the reading, our author calls this a mental u substitution, you might already have the answer down here. That's kind of weird as a strategy on an exam. So if I was doing this as an exam, I probably would be careful regardless. Let's let u be x squared plus 1. Just an ordinary u substitution. Du is 2x. Dx, or a half du, is x dx. So this x dx in the numerator gets represented as 1/2 du. There's now just a 1 in the numerator, and we specified our denominator should take the form u. That means it's a 1/2 natural log absolute value u. Can throw the constant there. And then finally, this is 1/2 natural log x squared plus 1 plus a constant. You recall if you want to drop absolute values, it's appropriate if the function is non-negative. Well, we've got all this together, so that's our right-hand side equals 1/2 natural log x squared plus 1 plus a constant. Here's where it starts to look like it's probably going to get a little bit messy, right? This is in implicit form, but we can solve this in explicit form. So let's take some more algebraic steps. If this was a real exam or final exam question, I think this would be most of the credit getting to this part right here. But we still have to push forward for the last maybe 1 or 2 points. The technique is left-hand side is now an exponent to the base c exponential. Same for the right-hand side. And there's an extra problem on that. If I have divide by 2 like this, I don't have a cancellation through the base c exponential. So maybe let's take one more additional algebraic step to solidify this better. Natural log absolute value of x. We really need to use properties of logarithms now. Clear out this, what's now an exponent on x squared plus 1. So natural log square root x squared plus 1 is much easier to work with now. Now go like that. Pretend we were doing that all along. Here's the base c exponential, just write it in. Cancellation does go this way appropriately. Still a little bit vague here. You don't necessarily want to show a cancellation like this on the right. Let's take one more step to say e natural log root x squared plus 1 times e to the power c. So we're just using exponent laws. A base times a like base adds the exponents. That's a good step to write in because the cancellation is just here. It's still e to the power c, plus c does not drop down. So now absolute value of y is way over here on this cancellation, root x squared plus 1. Let me write the coefficient in front though. E power c root x squared plus 1. This is an interesting coefficient because it can never take on value 0. Yet, we wipe out absolute values, we're going to have a plus and minus right here. And yet still, there's a particular solution that just occurs to me. There's one value of y that solves it as a constant function. Anyone see what it was? It is, yeah. If y equals 0, the derivative of y is 0 on the left. Everything on the right-hand side, because y is in a numerator, is 0. This is a particular solution. Over here, e power c, also written over here, is saying our constant is strictly non-negative in our solution. But then we drop absolute values by writing out y equals plus or minus e power c root x squared plus 1. Well, now this is saying the coefficient can be any real number except 0. But if a particular solution is 0 itself, that tells us this coefficient c right here, plus or minus e power c, can now be just rewritten as y equals, let's call it c1, root x squared plus 1, where c1 is in R. Any real number whatsoever qualifies. It's rolling in together this form of the exponential, the negative form of the exponential, and the fact that 0 qualifies. You can let your coefficient be 0. You're just picking up y equals 0 when you do that. So this one's kind of an excessively complicated at the very end. I feel like if you've got to just absolute value y, or y equals plus or minus e power c root x squared plus 1, you didn't see the particular solution, that would still be full credit on this kind of problem. This is just an introduction to differential equations. We haven't seen all these weird things in a full course for all those particular specific solutions. But any last questions at all, folks, for the separable equation on this one? Okay, we've got like 3 minutes and some change, so probably what we'll do when we come back on Thursday, I'll open up to the class for any specific questions you want to jump into. Then we'll just start reviewing, looks like chapter 11, the last part of the course. We might jump around since we're short on time. So if it looks like we're about to do a extra tricky looking concept question, I'll leave it up to the class. We may skip it for the concept computational ones, and I can come back to solve these. We'll just see how we feel about it when we come back on Thursday. Well, any last questions at all, folks, before we call it a day? Okay, have a great night, everyone. Thanks for the help with all those weird dropped values and odd algebra steps. Yeah, go ahead.
Well, we have to, like, if there's a particular solution for zero or for the differential equations, well, we have to add that.
If you've missed it, you wouldn't lose any points. I'm not going to make that a big part of the grading rubric on this one. Probably going to go for a more routine kind of separable one that doesn't have. Yeah, exactly. That's where the major emphasis is going to be. Because honestly, those are easy to miss, hard to spot, unless we're just in a course on this concept. Any other last questions? Okay, have a great night, folks. We'll pick this up on Thursday. Awesome, thank you. Any questions? Ah, did you take it in the classroom or?
That's a great one. I think I did take it here.
Gotcha.
The only one I didn't take here was two, because I took it early.
I'm gonna take a look into that. It is Kevin.
Yeah,
Kevin
actually, I'll ask this question for class.
and exam one. Yeah, I'm gonna hunt that down and let you know what I find.
Because I was looking through our emails, I didn't, maybe I got it back in person, but it's been a long semester.
Gotcha. I'll be able to hunt that down for you. I'll let you know on next class.
Okay, cool. And then I'll ask this stuff.
Sounds good. Yeah, I'm really kind of excited to take questions from the class to see specifically what people want solved. So I'm glad you've got one. Awesome. Yep, you betcha.